Okay, so I think I'm going to show you how to code the optimization problem today. But before I start, let me write down the formula first, and then so you can go back and forth the code and the formula when I do that. All right, so linear regression. So we have data xi, yi. So here data is from 1 to n. And what we want to optimize is the least sum square, right? Like the sum square. So we optimize the L, let's see, I'm just following the notation in my book. So I'm not gonna use M and B as I did last time. So we optimize this function. So mu is the slope and rho is the y-intercept. So this is yi minus xi mu plus rho square, where I is from 1 to n. I want to optimize this. So there are two methods of doing this. So Hess's and gradient descent. The Hess's method is finding the critical point. So critical point is mu zero. Let's say mu. Let's see, mu tilde and rho tilde is quite complicated. Let me write down all this here. So the sum xi square minus sum xi square over sum xi yi minus sum xi sum yi. So that's mu. And then rho is n xi square minus xi square, and then xi square yi minus xi yi. I mean, you don't have to remember this formula. I'm just writing down for my information, and also yi here. So you can find the exact point where this function is minimized. So we kind of explained why it's minimum, not maximum. And let's think about the gradient descent. And here is also the formula of gradient descent to find that. So let's see. So I'm going to start from mu 0 and rho 0. Mu 0 and rho 0, just random. And then update my mu I plus 1, rho I plus 1 with mu I, rho I plus h times the gradient vector. And I'm writing down the gradient vector here. 2 xi square mu I plus 2 xi rho I minus 2 xi yi. That's the first coordinate. And then second coordinate is xi mu I plus 2n rho I minus 2 yi. Okay. So that's a linear regression in two different ways. One is Hessian, two is gradient descent. Now let's write down the neural network and just, yes. Sure. Okay, is it better? All right. No, you don't have to write down if you have a book. Anyway, so let's think about the simple case. So we're going to work with the MNIST data, or handwritten digit data. And what I'm going to do is classify 0 and 1 image. 0 image and 1 image. I'll show you what it looked like. And we're going to use neural network. And here is our model. So we have x1 up to xn here. So these are image data. Okay. So image data consists of pixels, and the size, the number of pixels depends on the size of an image, and usually it's size of 14 by 14 or 28 by 28. So this is how much that is for each pixel. And then we're going to send this neuron to kind of an output layer here. And this output layer also contains the bias here, which is the constant. So y is w1 x1 wn xn plus b. So this is the simplest function we can think of, the linear function. And then we're going to use the activation function to get the final result. So activation function sigma is sigmoid function. Sigma y equals to 1 plus exponential y over exponential y. Or you can write it down as 1 over 1 plus exponential minus y. So I think this might be better because it calculates exponential ones. But it really doesn't matter, really. Yeah. So anyway, what is the loss function? So as I said, as in this case, the parameter is the slope and the y-intercept, not x and y. These are data. And here, x are the only data we can get. Y is the determinant variable. So what we can change is the weight for each input data and the bias. So we're gonna set our loss function. So this is called the function which you want to optimize as a loss function. That's why I used L here, but that's the name is not important. But anyway, so this consists of all the sets of this wi value and b. Okay, so here vector w is an abbreviation notation of all the pair of numbers from w1 to wn. And what is it? So first of all, let's call this TWB. Okay? So it's just a transformation of input neuron to output neuron y, and we're gonna take that as the first function, and then we're gonna send it to the activation function, and we have z. Now what we are doing here is we're gonna take the loss. We're gonna take the difference between the actual value and the real value. So this z is the real value. So this is what it's supposed to be, but our MNIST data has actual label of each image. So here L, Z, and Z tilde is just Z minus Z tilde square. That's what's going on. Yeah, so Z tilde is the label of the image. And this is either 0 or 1. So this is an image. This is an image. And for every image, MNIST data comes with the label, the answer to that image, which means that if it's 0 attached to the associated to image 0, then it's 0. Okay? So it's kind of obvious when you see the image that it's 0 or 1, but in the computer, you don't know, so you have to have an answer sheet. So Z bar is always 0 and 1, and Z here is the final result, the final output neuron of this neural network. So that's L. So you see what's going on. So this L is 1 by 1, maybe 1 by 1. And the sigma is also 1 by 1. How about this? This is n plus 1 by 1, right? So basically, this loss function takes n plus 1 parameter. So the x w1 to wn and b, so they're total n plus 1. And then make it into y, which is a single value, and then put it into activation function, and then computes the loss. Okay? So we're not going to use other method than gradient descent. So how does it work? So first of all, you start from the random, this b bar. So the random initial point, just random. Or you can just put it, take it as a 0, doesn't matter. So and then every time bi plus 1, you update this new value from the previous one, wi bi plus, actually minus, because you want to decrease the value of the loss function. The loss function actually measures what? The error difference between the actual value and real value. So you want to make it smaller as possible. So h times the gradient, right? So now we have to find what gradient looks like. So this is multivariable function of real value, but therefore, so if you take the gradient, it's same as taking a derivative. So what is the difference between gradient and derivative? Well, the gradient is the vector and derivative is a matrix. But if you have a function like this, so function like Rn plus 1 to R, then this is n plus 1 dimensional vector, and dl is n plus 1 times 1 matrix, right? So there's no really difference. So how do you express vector? It's just arrange all the n plus 1 values as a pair. And also in the matrix part, it has, sorry, it's opposite, right? 1 times n plus 1. So it's a row vector. So a single row and n plus 1 column, just like vectors. So you can just identify these two as the same thing. So when you think about the derivative of L, now you can use the chain rule, because L is really the composite of three functions. So what does the chain rule say? dl, d sigma, dt. That's the chain rule. So what is dl? L is this, right? So in fact, we don't have z tilde. So it's just a function of z, because z tilde is associated with the image and it's given as a data. So we know what this is. This is constant. So we actually have a value z, put it in, and then what comes out is the result. So the L is simply L prime, because it's a one-by-one one-to-one function. So this is 2 times z minus z tilde. And then what is the sigma? I think we mentioned this. Remember? Okay. So and then dt, what is it? So now this is a function of several variables, but there's only one outcome, one output. So there are n plus 1 variables, and let's take the partial derivative. So it's w1 up to wn and b, right? So this is 1 by n plus 1 vector or matrix, and you can multiply all these together. So these are actually just number. Just take multiple of two numbers with this 1 by n plus 1 matrix to get the gradient. Okay, so final result is just also 1 by n plus 1 matrix. You can consider this as a vector, okay, and put it into here. So 1 by n plus 1 vector. Okay, so I think I mentioned everything I need. So I was about to give you the example of application of gradient descent on linear regression and MNIST data imaging processing, and I wasn't able to show you full the correct result, so I'm going to have a supplementary video to make it up. So first, let's start from linear regression. So let me give you the diagram of our scatter plot for data here. So we have, as usual, import numpy as np and matplotlib as plt. And I'm going to I'm going to make artificial data about the high school GPA and the university GPA. So let's say our university GPA is X and high school GPA is Y. Oh, sorry, it's the opposite. So X is the high school GPA, Y is the university GPA, and we probably want the correlation between these two values, right? So I'm going to make a 10 number of subjects. So each subject is of each person and who got into the university with certain high school GPA. And I'm going to assume that my Y, the high school university GPA, is following a linear model which has the slope mu and y-intercept rho, and the slope is somehow around 0.5 and the rho is about 3, right? So, and then let's make our data. So the problem is our data has to contain some noise because there's always a human factor that nothing is going by the plan. So you might have a random person. So it's going to be a person who has high school GPA from 1 to 9. So if you want to randomize the number in between 0 to 9, then you can rescale your random number from like this one, rescaling by 8 and then add it to 1. Then your university GPA will contain some noise, and let's control our noise to range between minus 0.5 to plus 0.5. So I'm going to take a random number and then subtract 0.5 so that the range is now minus 0.5 to plus 0.5. So my university GPA will be basically the model plus the noise. So it's not going to be always the same. So I'm going to append my high school GPA to my list and university GPA to my list Y. So let's plot this out as a dot point here. And let's see what it look like. So you can see there are dots, 10 dots here, and each dot is a person, and the x coordinate is the high school GPA, y coordinate is the university GPA. There's some kind of correlation, but not strictly following on one line. So we want to find the best fit line that describes this situation. So we're not going to change the x or y, nor we're going to rerun this code block, because after we run this code block again, it will generate a random new numbers. So we don't want it. We don't want to change our list x and y. So we want to keep it. So we're gonna do the we're gonna try two different methods of finding the best fit. The first is using the Hessian. So we're going to find the exact value, exactly the minimum point where our local errors are minimized. So first of all, let's make an array of our list, np array of y, and then let's compute all these coefficients. So first of all, a is y squared, just as I described on the board, and the second one is x times y, and then third one is just sum of y. Sorry, so I just comma here. And the next one is sum of x, and the next one is square. Okay? And then there is a formula for the minimum mu and rho that minimizes the errors, the square sum errors, right? So it's n times b. So n is a number of data here, so it's 10. I saved it in the variables n, so I'm going to use this n right away. So n times e minus d squared, that's mu, okay? And then rho is E times C minus B times D, and N times E minus D squared. So I'm going to plot this out with the plotting of the data. So this is the data. And let's draw the line that is whose slope is mu and the y-intercept is rho. So t is the point from 1 to 9, the x-coordinate, the endpoints, and endpoints are 1 and 9. And then I'm going to plot the line by connecting the line for x-axis in t and y-axis as mu times t plus rho. So that is supposed to the right value, but we have a noise. So you can see that this line is what it's supposed to be, but you can see that they're off. No one is on the line because there is an error, human factors on it. And you can see that the mu and rho in this way is actually given as 0.49 and minus 0.49 and 2.9. So in the beginning, what we have done here is that we set the mu as 0.5 and rho as 3. And we kind of generated our data set by adding a random noise. And according to what is given in the data, we kind of backtraced what the mu and rho should be, and it was almost quite similar to what is defined in the beginning. So if the data, if the in the real situation the data is given already, it's the data that is given first, and you're supposed to find what is mu and rho, the slope and the y-intercept, by interpolating this data. And the reason why this is correct is that the mu and rho that I just initially set up is just artificial mu and rho in order to just make a data. So this one is the answer for our to this that describes the linearity of our data the best, because that gives the minimum error, the squared sum errors. Now we're gonna do a different approach. So instead of using the actual formula for the best fit curve, best fit line here, we're gonna use the gradient descent. So how does the gradient descent works? So first of all, you start from the random mu and rho. So so it really depends on what the performance of this gradient descent depends on what the initial value of your point is. But we kind of know that by looking at the data, we know that the slope is negative. So let's say our mu is -1, and it kind of seems like its y-intercept is around 3. So I'm going to set the rho to be 3. And the h, which is the step size, is going to be 0.001. So the reason why I just choose 0.001 is because I already have tested it out that this works the best. So if you have the step size h to be too big, then you're not going to get anywhere close to the minimum value. So you have, but if it's too small, then it takes tremendously many times to get to there. So you have to kind of balance between big number and small number that works efficiently and effectively. So I'm going to run this for 100 times. What I'm going to do is find the gradient vector at each mu and rho. So we already talked about the loss function, which is the sum square of the errors. And the new mu is the fourth coordinate of the gradient vector. And so new mu will be updated value of mu by subtracting the first coordinate of your vector. So first coordinate is 2 times e times mu, and 2 times d times rho, and 2 times b. And now second value of the gradient is similar. It's going to be used to update your rho, and this is 2 times d times mu and 2 times n times rho minus 2 times c. All right, so every time I update it, I'm going to send it back to our original mu and rho, so that the next time computing the gradient, I'm going to use the updated value. So mu and rho. So I'm doing 100 times, and I'm going to plot this out with the scatter plot of original data with the same method in space 1 and 9, and then plot t times, now using mu and rho as we searched in our new method. So you see that I initialized mu and rho again. I'm not using the same mu and rho I did in the previous code block, and then I updated my mu and rho, and I'm going to print out mu and rho to compare it with the above value. So let's run this block, and then what happens is it ran for 100 times to adjust mu and rho from -3 to -0.5 and 3. So it's kind of slightly changed, but not, I mean, so slope is changed a lot, but the y-intercept is not changed much because it's already the optimal value, as you can see from here, it's already optimal at 2.9. So it's kind of, not the same. It's not the same point as we found as an exact value, but you can see that it's very close. So if you take the right amount of step size and you do the gradient descent in the right amount of numbers, then you will get to the local minimum as close as you want. But you need to find those two things, how much times you want to run the gradient descent and how much step size you should take for each gradient descent. So I did it roughly, so I just took the rough estimate of my step size and rough estimate of count how many times of the gradient descent, but still I got similar result. And by looking at the picture, you cannot tell the difference too much, right? So that's the application of gradient descent on the linear regression part. And now I'm going to move on to the application to neural network using the MNIST data. So let's try to take the TensorFlow here. So the MNIST data can be downloaded on the web, but in TensorFlow package, there is a built-in function that loads the MNIST data set. So I'm going to import the MNIST here, and then also import NumPy and Matplotlib. So I already did it, so you don't have to import the NumPy and the Matplotlib again if you follow the linear regression part before. But I'm just doing it sometime in the case that someone who just jumped into this part right away. So first of all, let's import our training image and training test image and training image. So train image set with the training label set, and test image set and test label set, and using load data function. So I'm going to show you how many there are. So train image, the number of training image, and number of test image. So let's run this part, and it's downloaded. And you can see that there is number 60,000 and 10,000, right? So there are 60,000 training image from 0 to 9 and 10,000 testing image from 0 to 9. We're not going to use all images of 0 to 9. We're only going to use 0 and 9. So we're going to separate out the image that is about 0 and 1. So in the test image 0 and train, sorry, not testing. So train image 0 and train label 0 and 1, I'm going to make a new list. And for each train image, if it's labeled is 0 or 1, then I'm going to throw that into my new list. Image 0, append train image I, and also throw that into label set, append train label I. So we do that for the testing image. I also need 0 and 1 for testing. So I'm going to sort it out, and for I in the range of length of test image, if the test image I is 0 or, so sorry, not image, it's a label, is 0 or 1. Then throw that into test image in label 2, test label I. Okay, so let me print out the number of training image and testing image of 0 and 1. So the length of train image 0, 1, and length of test image 0, 1. Let's count this. So there are only 12,000 images of 0 and 1 and 2,000 images of 0 and 1 for the testing, right? So there are about 1/5, but not exactly 1/5. Okay. So what we're going to do is training a model. So what is our model? Our model is just the neural network based on the linear formula, right? So in the linear formula, what we need is the weight and bias. So I'm going to just put my weight to be a, you can put a random number, but so that's where our coding went wrong in our class. So the problem is, if I use the random number for weights and random number for bias, then when I compute my output neuron, it gets too large, or and then the sigmoid function cannot correctly adjust the number in between 0 and 1. That's because I didn't rescale my image into smaller sizes. So this image of 1 and 0, or other images from 0 to 9, is of size of 28 by 28, which contains 784 pixels. And each pixel is about the number from 0 to 255. So even though I rescale it, the number of pixels is too much. I cannot handle these 784 numbers at the same time. The input neuron layer is too big. So I need to rescale it, but I don't want to right now because I just want to make it a simple model of my neural network. So instead of make the number of neurons smaller, I'm going to set my weight to be start as zeros, okay? And then I'm going to gradually increase my weight or decrease, if it's the case, to adjust it to minimize our errors. And bias also 0. So we're going to set it to be this way. All right, so let's measure our performance of model here. So here the model is this 0 function because weight and bias are all 0, but let's do it anyway. So I'm going to count the number of success here for all the test data, length of test image set of 0s and 1. And I'm going to compute output neuron of test image. So when I do compute the test image, I first have to flatten out these two-dimensional array into one-dimensional array and rescale it, because I said it's a pixel from 0 to 255. It's too big, and I have to make it into number between 0 and 1. So divided by 255. And y is a linear function, so it's just weight times x as a dot product and add bias. So at this moment, whatever I do here will be 0 because weight and bias is 0. And also let's compute it with the sigmoid function to scale it between 0 and 1. Again, since it's always 0, the exponential 0 is 1, so it's going to be just 1 over 2, right? So anyway, I'm going to just show you how it's done as if it's not 0, as if it's a random number. And I'm going to collect the result based on the size of z. So if z is bigger than 0.5, I'm going to call it 1. And if it's not less than 0.5 or equal, then I'm going to decide that the image is labeled as 0. And I'm going to compare my result with actual real result. So the real result is stored in the label set 0, 1 here. And if that's the case, if they are the same, then I count the number of success. And let's print out number of the percentage of success. So we have here. So it's about 46% chance of success, right? So it's basically coin toss. And now let's train our model. So I'm going to use my training set, train image 0, 1, And then for each image, I'm going to adjust my weight and bias slowly. And first, what I need is have an input image as a pixel and flatten out and rescale it. And then I'm going to put this into our output neuron with weight and bias, using weight and bias. So when I run this loop for the first time, it will be y equals to 0, and z will be just same as 1 over 2. So nothing special, but after I done that, I'm going to compute how much weight and bias should I adjust. So the amount of adjustment of weight is computed by the chain rule. So because it consists of three functions, the loss function, the weight sum bias is so error square sum is computed as a composite of three functions, as we mentioned in the blackboard. So it's going to be first difference between the actual label and our estimate times the derivative of sigmoid function times the derivative of linear function. That's the amount of change we should give to the weight, and the amount of change that we have to give to the bias is except for the last part, because bias has no coefficient here. So we're going to update our weight and bias, and that's it. So for our information, let's see how the weight is changed after we done that. So run this. There's some error. The weight is, so I forgot to put the capital X instead of just X. Okay, so there's a small typo here. All right, so you can see that the weight was originally 0 because that's how we defined in the first place, and we didn't change the weight here. We changed the weight here by using the gradient descent, and you can see that the number is now, it could be negative or positive, but all different, right? Basically point something, right? Now, it's too long because there are 780. So let's run this code blog again to get rid of the printouts. Now, using this weight and bias, I'm going to see the performance of my model. So just model is a function. So I just adjusted my function by changing my bias, which is coefficient. So I'm going to use the same code block, exactly the same code block, but when I run the above code block here, the weight and bias was 0. But after I run this code block, the weight and bias are updated. So this one will give you a different result. So now when I run this, it says 99.952. So which means that it's almost 100. It's almost accurate, right? You can see that out of 100, almost 99.9% of the image has been labeled correctly. I mean, you made the result, which is same as the given label. So let's see if let's see what happens when I what was the image that we missed. So if the result is same as the label, then we count that as the success. If it's not, then I'm going to print out that image, the image that we failed to label it correctly. So this was the image. So it's kind of colorful, but if I make a CMap to gray, it's going to be labeled the correct way. So it's an image of 0. We know that because we are human, and machine doesn't really know that because our model classified this image as 1, but it was really about 0, right? Well, there's a good reason, because there is a dot, unnecessary dot, that confuses computer or confuses our model to correctly label this as 0. So it makes sense, right? So this is not really a good image, or I would say it's not a good image to put it into the model, but it's not that the image is wrong. It's because our model is not accurate enough to classify this kind of image here. But it's understandable. What we have done here is just train the model for each image, and this is very, very rough kind of training, right? We used one image for one step of gradient descent. And usually when you train your image in a neural network, you don't do that. There are many techniques of using all potential power of this image data set given in given in our hands. So there are we're not using those kind of technique here. I'm just showing you the simplest and the most intuitive way of implementing the gradient descent in the neural network. Yeah, so I hope that this work helps. And if you're doing the project 6 in the final presentation, then I hope you can do something more. For example, you can change your data set, or you can change your technique, then and find anything interesting is obtained.